All right. Hello, everyone. I would like to welcome you to the next webinar on ATENA. So let me just first, of course, welcome you again. And I would like to summarize the rules that I would like everybody to follow during this webinar. So please have your microphone turned off. In case you have a question, please write it into the chat window. And I will be following the chat window and try to answer the questions as they will appear. So please do not wait till the end of the webinar and ask your question anytime you want. The webinar will be recorded, and the recording will be then available on our YouTube channel, and also you will receive a link to that. So let me first start sharing my screen. So the topic of this webinar, I should go to the first page, is about post-processing and how to properly understand the results and evaluate the results from nonlinear analysis in ATENA. So this will be the focus of our webinar today. And well, let's a little bit first summarize what we are trying to do with nonlinear analysis. So with nonlinear analysis, we try to understand better our structure behavior. So as you can see, when we think about concrete and we are designing concrete, we typically have our rules based on experiments like you see on the photos here. And these are typical laboratory experiments that were used in the past and continuously to develop some rules and formulas which are often empirical to understand the behavior of our structures and evaluate the strength of the material. So this is done by these laboratory experiments. And of course, in practice, we need to apply it to sometimes to a very complex situations which are very far away from the geometries and the sizes of the specimens that we typically test in the laboratory. Nowadays, we have these very fancy architectural shapes also. And also recently, this technology of 3D printing, which again is something which is not really which does not really fit into the current design formulas which were developed mostly for beams or slabs. So we can use nonlinear analysis. We are using finite element method. We have structure divided into finite elements. Inside each finite element, we are considering nonlinear laws. So typically, we should perform the analysis that we incrementally load our structure, like it is shown in this graph at the bottom left. And we do in an incremental way. We always assume elastic predictor, and then we correct based on the stresses which are calculated at these integration points. So this is just, let's say, some understanding. So what we typically do is that we have our structure and we load it all the way to failure. And, so we, in the end, have this kind of typical diagram. Yes, we keep loading our structure all the way up to failure. But this loading history is actually important part of our analysis. We need to somehow define it such that it reflects the current situation or the real situation as much as possible. So what I'm showing now is this analysis of this kind of beam. So this is this example. It is a continuous beam, but then there is a failure in this left span. And we need to define our history of loading to somehow represent what will be happening in reality or in that we want to consider in our design. So what we recommend typically that we first apply. We can divide our loading into intervals. Those of you who are familiar with ATENA science, you know that the loading is defined by intervals. So it is good to define a first interval that represents, or let me put it like this. We have to understand that in the end, we want to verify some load combination. For instance, this load combination, 1.35 times dead load and live load with the coefficient of safety for the loads, partial factor of safety 1.5. Yeah, so we have this load combination that we want to verify. So of course, one possible way would be to apply this whole load combination and keep increasing it until we reach this value, and then maybe continue to overload. But what we typically recommend is do not load directly by all loads, but try first to somehow apply loads in some representative way. So typically what we first have is the dead loads. So we first apply the dead loads with the multiplier 1. And then we apply other, so this might be the self-weight, then we have other permanent loads, and then with the third interval, the live loads. First, recommend everything to apply with a load factor equal to 1. This means in these 3 intervals, we will somehow drive or go with the structural loading through some representative steps. It might be interesting to see really what is the behavior of the structure just from the dead loads, just from the permanent loads, then permanent loads plus live loads. Okay, so then, of course, we need to reach this required load combination, 1.35 times 1.5 times live load. So then we need to apply whatever is remaining to reach this load combination. So this would be, let's say, in this interval number 4. And then we need to, or it is usually advisable to load the structure all the way to failure so that we can really understand the failure mode of the structure. So this will be this 5 interval where we apply all the load combination with all the load factors, and we can keep increasing that. So if we look at this diagram, we then typically can plot the total loads. Of course, it is up to you or up to the user how to define them correctly. One way you can do that is, for instance, to monitor or to report the total forces acting on the structure and some maximal deflections. So as you can see, as we keep increasing the loads, we are passing through these individual points. So for instance, this interval 4, this level 4, this green line, would correspond to the characteristic load combination where everything is with the factor 1. And then this red line would correspond to the design combination. And whatever we have on top is, let's say, additional safety factor. Of course, this is something we can use or also, for instance, to cover for the model uncertainty. This nonlinear analysis, we need to consider some modeling uncertainty. This, of course, was discussed in some other webinars we had in the past. So this is an important part, that when we are analyzing our structures, of course, if we are simulating an experiment, it is quite clear how to apply the loads. But if we are using nonlinear analysis to verify some design combinations or assess existing structures, we need to think about how to define properly in a representative way our loading history. I see there is some question. So there is a question by Yahaya Kurama. Do we need to analyze the failure by applying displacement, or can it be done by applying load? Well, this is a good question. Well, of course, if we are simulating an experiment, then often we are loading our structure at a single point. So if we are loading our structure at a single point, it doesn't matter whether we load by displacement or by forces. So we can do both ways. In this case, if it is at a single point, it is maybe advisable to apply displacements because the analysis is then more stable and easy to calculate. But of course, if we are considering real design situation, it's not possible to change the loading to displacement control. If we have body forces, some earth pressures or pressures on the surface, it's not possible. It is not possible to change it to a displacement type of loading. So we need to load by forces. And then, of course, it's a question, how can we go to post-peak if we are loading by forces? So that was actually a good question because it reminded me that I should mention that in order to really calculate failure load, we cannot use the standard Newton-Raphson method in ATENA, but we should switch to arc-length method. Arc-length method allows us to start decreasing the loads when we go to post-peak. I don't want to discuss here about the arc-length method, technically what it is about, but let's just say that it is a method for that even when we apply loads as forces, it allows us to detect that there is a peak load, and at some point the program automatically starts decreasing the forces. So this means that when I'm applying the loads, this loading history in these intervals, I should at some point when I am expecting some interval, that in some interval I may reach failure, I should not use Newton-Raphson method, but I should switch to arc length. So typically with this loading scenario, in this last interval, I will not use Newton-Raphson method, but I will switch to arc-length method. In ATENA, you can do that in the solution parameters. So that was an important question. Marcos Silva is asking, does the program understand that, for example, in the third interval, the dead load, interval 2, is still acting? Yes, this is, ATENA software is incremental. So whatever forces you apply in one interval, it stays there. If I want to remove it, I have to apply it again with the negative sign. So typically you can apply it again with the multiplier -1 if you want to remove the load. So just to repeat it again, the forces that are applied in ATENA are always incremental. That means whatever you applied stays there unless you specifically remove it. This is of course not true for the supports, yes, because sometimes you want to remove the support. So the supports are of course not incremental. They are always acting if they are applied. If they are not applied, then they are not there. Also, some other loads in ATENA are not incremental. I don't want to go into details, but for instance, the fire loading is again a loading which cannot be incremental because it is either acting or not acting. It cannot be subtracted, yes. So I think this answers the questions that are in the chat window. So I can continue. The next slide. Again, this is so this is again the same thing, but now I want to emphasize how do we detect the failure. Important now part of the understanding the results is to understand what is the failure mode. And of course, it might sound easy to recognize it, but in reality, often it may be not so easy. So let's talk about how to recognize and identify the failure modes in ATENA. So one good thing that I recommend always for any time you start calculating, always look first at the deform shape. This has nothing to do with the failure mode actually. I would always recommend immediately after you have few steps calculated in ATENA, always plot the deform shape and maybe enlarge the deformations, scale up the deformations so that you clearly see how the structure behaves and whether it makes sense. Because it can help, it may help you to discover some mistakes in your model. You might see some parts which are suddenly overlapping each other, so you will notice that they are not properly connected together. Or you may see that some parts are not supported properly. So important first thing you should always do, look at the deform shape, rotate the structure, look from various sides, and really check whether the deformation makes sense. And now about the failure. You know, in ATENA you can display cracks, you can display crack width. So this is of course first information about the failure mode. So this will tell you that there is a cracking. Yes. Of course, cracking often doesn't mean failure. We are dealing with concrete, reinforced concrete. ATENA is mainly for the analysis of reinforced concrete, as you know. So in concrete, the cracks occur quite early, and definitely it doesn't mean that there is a failure. So cracking is a good indication that some damage is happening, but it doesn't mean necessarily that it is a failure. For instance, in this case, it looks like there is a shear crack developing, but we have stirrups typically in these kind of beams. So the stirrups will take over, and that's why we have reinforcement in concrete. So the reinforcement will take over the stresses from concrete, and the structure should be still fine. So that's why if we see cracks somewhere, the next thing we should look at is to look at the stresses in the reinforcement. And we could check that these stresses are below, for instance, the yielding. In this case, we see the yield strength would be around 500, so we are still below, although some parts of the reinforcements definitely crossing near the cracks where the cracking is occurring. They are higher, of course, but still no yielding is occurring. If we want to really check whether there is yielding, better than looking at the stresses, which might be sometimes difficult from the colors to see really what is happening. So the best way is to look at the plastic strain. Plastic strain XX, because reinforcement is always one-dimensional, unidirectional behavior. So what is only important is the XX component. And if you look at the plastic strains, this clearly gives an indication whether there is some plastification, reinforcement yielding. So in this case, for instance, you would see, okay, there is reinforcement yielding here above the support, which is, let's say, meaningful and possible. And this can indicate that this section reach its limit strength. So this is, let's say, the second important thing we should look at always when trying to understand the behavior of our structure is to look at the plastic strains in the reinforcement. So, and then the third value to look at is to see whether we have concrete crushing, whether we have crushing of concrete. Of course, one way to look at whether we have crushing of concrete is to look at the stresses in the concrete. But this is not easy to understand what is going on, because we have to understand that in ATENA, typically we have 3D structural behavior. So we have a 3D state of stress. So this means we may have some confinement, and sometimes we may have higher stresses than uniaxial compressive strength. this still does not mean necessarily that the concrete has reached its limits. The only or the best way how to look at to really understand whether the concrete has reached its limit is to look at this equivalent plastic strain. This is one quantity that can be showed in ATENA in the for instance the contour areas. And what is this plastic strain? It tells you how much plasticity or how much yielding has occurred in the various areas. And well, if I briefly remind you of the concrete material model, it consists of a fracture part for cracking and a plasticity model for crashing of concrete. And this plasticity model has a hardening part, which is shown in this graph, and then softening part. In the hardening part, this development of, or this hardening is controlled by plastic strains. And this limit, this is the point when we reach compressive strength, is called epsilon CP. So it is a parameter in the software. So you will know, and this can be compared with these equivalent plastic strains. If we see that these equivalent plastic strains are below this epsilon CP, so let's say in this model, the epsilon CP has this value. So we know that whatever colors are above, it's going to negative, so kind of below actually. So whatever it has is between yellow and blue is after. So the epsilon CP is higher. So we are somewhere here. So we are in the softening. If the equivalent plastic strain is lower than this epsilon CP, we know we are somewhere here. So this is the best way how to really understand whether the concrete is in the softening, basically failing, crushing, or whether we are still in this hardening stage. Okay, so this was just the reminder. Yes, we have this plastic fracturing part, which takes care of the crack development, and then we have this compressive hardening part, which controls, or this plasticity model, which consists of hardening and then softening. And the important parameter is this epsilon CP, which is the point when we reach the compressive strength. And of course, due to the structural state of stress, the stress may be higher because we have the 3D effect due to the shape of this plasticity surface. So the best way is this look at these equivalent plastic strains. Another nice feature in ATENA is now that we can also define cuts and then generate the cuts through the section and use them to evaluate these traditional engineering quantities like moments, normal forces, or shear forces. So so this was, let's say, some presentation at the beginning to introduce the topic a little bit, and maybe I'll switch to program and on some examples show it again in more detail. And before I do that, I'll check whether there is any question. Okay. Michael Halgren is asking, what is really the difference between equivalent plastic strain and the principal plastic strain? Yes, it's a good question. Actually, the equivalent plastic strain, each material models use some equivalent quantities often. In ATENA, this equivalent plastic strain is defined as a minimum of principal plastic strain. So actually, you will see that the equivalent plastic strain is equal to the minimum plastic strain. So you can look at the both quantities. All right, so let me now show some example, and let's look at these things that we talk about again. The ATENA window. So what I'm showing, you may recognize, this is the ATENA Studio with post-processing of one example. So you see, typically, again, I recommend that every time you run ATENA analysis, always define some monitors. So, and these monitors then are usually good to show them during the analysis. In this case, I have a one monitor here measuring the maximum deflection. This is shown on the horizontal axis. And then I have a monitor which monitors the applied load here in the middle. In this case, coming back to the first question, because it is a simulation of an experiment, and experiment is in this case loaded by a single force. So it is better to control the analysis by prescribing displacement here. If we are prescribing displacement, then we should put a monitor monitoring reaction, because if we prescribe displacement, then as a result, the force is actually in the reactions. And this is plotted on the horizontal axis. And you see first there is elastic behavior, then we see some nonlinear effects up to the peak, and then we go to post-peak. Here, because in this example, I am applying displacement, that means I'm moving along this axis, prescribing the displacement, and always the result on the vertical axis is the reaction or the force necessary to create this deflection. So I can easily go to post-peak. I think you can understand if I keep increasing loads, I will be applying forces. Then at some point, if I apply force higher than the capacity, I cannot reach an equilibrium. And this will show itself in the analysis as, the analysis will keep running, the displacements will be always increasing, the convergence cannot be reached. So if I would be loading by forces, I will have to use arc-length method to go to post-peak. But in this analysis, I am using displacement control, prescribing displacement, so I can use the Newton-Raphson method, and I can calculate post-peak without using arc-length method. So now I'm in the post-peak. Nicely, I can see, you see the deformed shape. Somehow it seems like there may be some shear crack even. So how now to understand the results? Yes. So of course, one way, as I was talking to you, would be to print or to show the principal stresses to see whether we have crushing of concrete. But as you see, it doesn't show much because the scale is somehow damaged, or well, it seems like damaged, but actually it is affected by the reinforcement. And then that's why it is good to create an activity which really represents what is going on. So in this case, I would recommend that we go to activities and I create an activity which will contain only the concrete elements. So I create a new activity. I can call it concrete. And here in the materials, I can see which is my concrete material. It is this FC25. So I can activate that and I do OK. And now it looks much better, yes? You see, indeed, now the stresses starts to be reasonable. You see, I have stresses between, 6 to 38 minus megapascals. So this might say, okay, I have crushing of concrete, because what is the compressive strength in this case? I go back to the preprocessor. And I will check the material definition here because I forgot it myself. So you see the compressive strength here is 26, yes? So 27. So how come we have higher? Actually, what you see, there is somewhere some points which have higher. That's because here, when we are applying the support, of course, there the material is constrained, and due to 3D effects, we might have even higher stresses than concrete. So this is what I was talking to you, that looking at the stress by itself is really a not good good information about what is happening in concrete, because here we have some higher stresses, and in these yellow areas, it seems like, okay, it's good. There is just -10. Yes. So we would think, oh, okay, there is nothing is happening, but this is not true. We have to understand we are in post-peak, and actually the stress is lower because it's actually crashed. Due to softening, the material has lower strength. So the best way now how to look at it is really to look at this equivalent plastic strain. So if I look at this equivalent plastic strain, where is it? There it is. I do apply. Okay, now you see what is really happening, and it nicely corresponds to the deformed shape. So indeed, I see I have a crushing here, a compressive crushing next to the support. Also, it is good to understand what is the total shape of my structure, because I selected only the concretes. I'm somehow missing the remaining information, so it is good to use this button, Draw Full Model Outline, which now shows me where I have these additional parts of the structure, especially these loading plates. So I can nicely see now that the crushing occurs next to the loading plate. And here are the support plates. So this is so what I usually recommend when evaluating these results, to look at these these equivalent plastic strains. And in addition, it is good to modify my scale, not to use the standard one, but to have a user one. I would also like to put red on top here and blue at the bottom. But because I know what is this critical value of the epsilon CP, so I would say I want to set up my scale such that whatever will be red color will represent this concrete where it fully crashed. So now, whatever is above this value, which we can see if I look in the material definition, so I'm switching back to the preprocessor and I can check those material parameters. And if I go to the compresses, you will see that this is actually this epsilon CP I was talking about, which identifies the crushing limit. So now I can see, okay, so everything which is blue is a crushed concrete. And you kind of see that it started as a compressive crushing here, but also somehow kind of a shear failure developed also with maybe some crushing of the compressive strut. And let's see, so now it is clear we are at the post-peak, we sort of understand this behavior, and we can even go maybe to some different steps to see what happened when we were at the peak. So the peak is about, I can move with my cursor over the graph. This will tell me what is the load step when I am at the peak. So it is around 170. So I can go to this step. And yes, and now we understand it even better. Yes, indeed, we see that the failure started by reaching this crushing limit on this top part. And then, of course, due to softening, it's somehow localized in this area next to the support. And then it's sort of somehow propagated in some kind of a shear failure as well. So this, we really see what is happening in concrete. So we might say, okay, this is a typical example of a compressive crushing or compressive failure of a beam. But just, it is still good to confirm that. And we can we should look at the reinforcement. Oh, this is not it. This one. So we can, of course, either here there is a special fast selection to show only 1D elements, that is reinforcement, or we can again use this activity, Also, I like to use this checkbox, draw full model outline, so that I can very well see how the reinforcement is oriented inside our model. And yeah, and I told you, to understand what is happening with the reinforcement, we could look at the stresses, of course, but sometimes the stresses, especially, for instance, the reinforcement fully ruptures, they don't tell us that much. Here we see, of course, that all this reinforcement is highly stressed. We see that some the reinforcement yield limit is 500, so we see some part of the reinforcement is above this. So we could actually now modify I would propose to modify our scale to really see where is this limit of yielding. Of course, one way to look at it is to look at the plastic strains in reinforcement. If there is hardening, we can also look at it in this way, whatever is above 500. So we see a lot of reinforcement is yielding, but in this way it is somehow seems like very smeared, not really telling us still much. So again, better to look at these strains. Of course, normal strains would also give a good information, but maybe usually better are plastic strains. And now, of course, I need to switch to the standard color. And now it is much more understandable. Yes, we see clearly that there is some yielding of reinforcement in these stirrups where this cracking is developing. And if I go even farther on, we see it is more pronounced. Yes, so you remember in the previous, it looked like actually the more failure is on the left side, more yielding of reinforcement, but now clearly we see that the failure really localized on this right part. There is this diagonal crack showing the plastification of the reinforcement, and also we have a yielding of the reinforcement in compression. So, and we should not. So these are the most important aspects how to understand the results. Look at the plastic strains in the reinforcement. Look at this equivalent plastic strain in concrete. And of course, another way how we can look at it, we can also look at the cracking. But as I told you, the cracking is always good to look at, interesting to understand. But it is usually not the best information about the true nature of the failure mode. So if we look at the cracks, I'm sorry, we can, I open a new window and I use this crack toolbar to show cracks. And again, something I want you to emphasize, if you display all cracks, typically the figure is very misleading. Yeah, sometimes you see cracks everywhere. So I usually recommend to use only the first crack, because this is usually the major crack. In addition, if we draw the cracks together with the mesh, sometimes it is confusing what is a crack line and what is a mesh finite element boundaries. So I recommend in the view style to switch to solid with outline. So this starts to be better. But even better is usually also to put some limit on crack width. So the typical limit I recommend is something like 0.1 millimeter, which is the typically smallest visible crack. And once you do that, you see the cracks starts to be much more meaningful, and it will give a better information about the localization. So you could play with this limit. So I really recommend every time you are trying to make some nice figures for publication, play with these settings. Definitely, I recommend to put a minimum crack filter. Also show only the first cracks. Those are usually the major cracks. Of course, now you may say the cracking is still somehow not so nice. That's because we are already quite far into the failure mode. In addition, this failure mode is not so much about cracking. It is more about crushing of concrete. But if we, for instance, go to the peak, you will start to see, yes, much better and understandable view. We nicely see these bending cracks originally, then they changed to shear cracks. The shear cracks really did not fully develop. There are several of them because they are nicely addressed by the reinforcement stirrups, which took over. So we don't have a single crack, but we have more like many parallel cracks. So this was about these failure modes and how to understand the failure modes. Let me check if there is any question. Bogdan is asking, why is mandatory to define monitor points in first interval? Yeah, that's a good question. This is a little bit because of Git, yes. Well, that's because we want the monitors to be there from the beginning, so that's why they are requested to be in the first interval. But also I want to bring to your attention that once you finish your analysis, you can define a monitor in the postprocessor. You can define a monitor request, which can then extract other monitors which you originally didn't think of, which is often the case that you perform analysis and then you say, oh, I would like to extract some data from some quantity at some location, which and I don't have a monitor. So you can do it in the postprocessor as well. And how you do that, it has actually involves typically two steps. Here in this selection manager, you define some selection, and then you define a monitor using this selection. And when you do the monitor request, it will extract some data from the calculated steps. Of course, it can extract the data only from the steps that you have saved. Yes. So if you use this option that you do not save all steps from your analysis, then of course you cannot recover the monitors from those data that you didn't save. But if you are saving all data steps, then you can recover the monitors from the postprocessor. Kurama is asking, how do we select an appropriate episode CP value? Yes, this is this is good question, but of course I mean, I think it's quite clear what this epsilon CP means. Yes, it means the amount of plastic strains if you make a uniaxial test. This is the amount of plastic strains when you reach the peak. So if you have a test, then it's quite easy to extract whatever, you just divide compressive strength by Young's modulus and subtract that from the total strain value at the peak, and you have this epsilon CP. So either from test, but if you don't have tests, and maybe you are using some code definitions of material properties, then typically in the codes you also have strains at the peak, at the compressive strength. So again, from those strains you can calculate this epsilon CP. Michael Hallgren is asking, so according to the concrete model, the ultimate plastic strain at initiation of crushing is constant and independent of constraints or 3D compression. Yes, this is true. This is true. There is another model because this sometimes in a 3D configuration, this epsilon CP basically should be bigger. And there is another model which has this better. So in ATENA, there is this cementitious 3 material, which has a better definition of this basically of the hardening in the multi-axial state of stress. But in my analysis, I'm usually finding that the difference is not so big. But if it is very important for you, then you should use the cementitious 3 material, which is a little bit more complex. It also requires a little bit finer load steps to have a successful and robust solution. And Bogdan is again asking, I see that you have a lot of iterations in the load steps. Is the step or iteration convergence a very low value? Well, in this example, you are right. In this example I was showing here, I was using 400, and you can see in the post peak, it was not enough. Yes. And in this case, I was using so many iterations because in ATENA, you have always two possibilities: either use elastic predictor or use tangent predictor. In this case, I was using the elastic predictor, which is also a little bit faster, more robust. So sometimes if I really want to go into post-peak to have a very robust solution, and it is a small example, it's easy to make put more iterations to be sure that and use this elastic predictor to have a the most robust solution. Michael Halgren is saying, but according to EC2, the strain capacity increases in multi-axial compression stress. Is that neglected here?
I think you answered the question already.
Yes, I think, yes. It is true, yes. It is somewhat neglected and, let's say, conservative here. Abdin is saying, when you define the stirrups and its geometry, are these stirrups directly in contact with main reinforcement? Well, of course they are not, yes, because if you are, for instance, if you look at this beam, and I let's say make it transparent. So you see the reinforcement here, and you see the stirrups, and because the reinforcement is represented by its center line, as well as the stirrups, there is a little distance. So I'm not sure if I understand exactly where the question was going at, but you see there is a little bit distance between the reinforcement because they are represented by their center lines. But if you are concerned about this, that they are not touching each other because in the reality maybe they may be welded or something, well, it is not really a problem because the reinforcement are connected or the reinforcement is always constrained to the surrounding elements. So through these constraint by the surrounding elements, actually they are effectively more or less connected. Unless, of course, there is an element boundary between them, then they could, let's say, separate. Another question is by Kurama. For cracking, what is the difference between COD1 and COD2? Okay, that's a good question. In our fracture plastic model, we can have up to 3 cracks at each point. And they can be, and so the program always looks for next crack, and always, so we can have maximum 3 cracks, and they will have to be perpendicular to each other. So So this is the difference. And the COD1 is always the crack opening displacement of the first crack. COD2 is the COD crack opening displacement or crack width of the second crack. And usually the cracks are arranged such that the first crack is the one that occurred first, the second crack occurred second, and so on. Usually the first crack is the most important one, and usually the most with the largest width. But this is not does not have to be like that always, because if we have some cyclic loads or we have a very complicated stress path, it may not be the case. Yes. So as I'm saying here, typically look at the first crack as the most representative one. It is the situation in, let's say, 90% of cases, but not everywhere. Sometimes the best crack might be the second one or the largest crack. Fasil is asking, how is damage in concrete and steel defined? Especially important cyclic modeling. Well, I am afraid we are a little bit running out of time. This is a very complex question. I could start talking about the model of concrete. So I would recommend either look at some of our YouTube webinars or presentations in our YouTube channel on this topic, or look at the theory manual. There is more description about our concrete material models. How can we calculate the actual forces in the stirrups which are in critical sections? Well, as I told you, in this case, I could here, where was it? This one. I could, plot the reinforcement stresses. So I know now that the critical section in this one, and if I plot the stresses there, I can see what are the values there. Yes. And I can, make a selection, print them out. So if that's the question, well, the other thing I wanted to talk about today is this last option, how to calculate these integral quantities. So at least I will show it briefly at the end. So what happens is that it is sometimes good to evaluate these quantities. And you can do that in ATENA under this second toolbar. And there is this option cuts. And it works such that you first define a plane, which I defined here. So this is the initial cut I define. You can then see there are we can also use these cut definitions to plot some stresses on them or whatever quantities we need. But we can also use this cut and this plane generator where we say, I want to generate 20 planes starting from some location, or I can pick a point. And you see it generates additional cuts, and then I can integrate the stresses along these cuts by this evolution 1D. Then I can say, okay, what kind of quantities I want along these cuts, and this I can use to create these kind of integral quantities. However, I want to bring to attention that we need to understand that these internal forces are calculated by integration of stresses. And the stresses, especially if we have a little bit coarse mesh, are not so accurate. You can see that the moments are typically quite nice because the normal stresses are usually quite well represented. However, the shear forces are not so accurate. You might see some jumps, especially if there is some cracking. Typically what you can see, if I go to these parts where we have more or less elastic solution, they are much better. But if I am in the post-peak, where we have a lot of cracking, the results may not be so accurate. And this also gives maybe an answer to the previous question. Here you can see if I make a cut and the cut is passing through reinforcement, I have this additional information about the value at the reinforcement. So for instance, if I would change my quantity here, currently it is showing the equal plastic strain, but if I, for instance, switch to stress, maybe the first component of stress, it then shows me what are the stresses, and you can see here the stresses in the reinforcement. Yes, so this is maybe also answer to the previous question. So this is another way how to get these reinforcement stresses at some most interesting and critical sections. Okay, yes, there are only some thank yous. So I thank you too. And we are coming to the end of my presentation on of this webinar. So I hope this helped you a little bit to see how to in the best way, how to evaluate the results from nonlinear analysis in ATENA, and to understand the failure modes and some possibilities of output of results. So thank you again for your attention, and I am stopping the recording.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.